question is whether the ground rod is necessary given that its resistance is over 100 times that of the waterline ground. What does National Electrical Code, or NEC, Section 250 say about this situation? National Electrical Code Section 250.52 states that a ground rod is not required if there is a metallic water piping system that complies with 250.52. In the described scenario, the water line ground has a resistance of 0.3 ohms, which meets the requirements of 250.52. Therefore, the ground rod is not necessary. Let's delve further into what NEC Section 250 states. NEC Section 250.52 states where the grounded conductor is connected to the grounding electrode conductor and the neutral conductor is also connected to the grounding electrode conductor, a grounding electrode system shall not be required where all of the following conditions are met. The metallic water piping system complies with the requirements of 250.104a. NEC Section 250.104 specifies the requirements for metallic water piping systems to be used as grounding electrodes, including firstly, the piping must be continuous metallic, secondly, the piping must be in direct contact with the earth for at least 10 feet, and thirdly, the piping must be effectively grounded. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical wiring, overcurrent protection, grounding, and installation practices. It is published by the National Fire Protection Association, or NFPA, and is widely adopted in the United States and other countries to ensure electrical safety. Article 250 of the NEC is specifically dedicated to grounding and bonding. Grounding is a critical concept in electrical systems, and it involves creating a low impedance path for fault current to return to the source. This path helps to ensure that overcurrent protective devices, such as circuit breakers or fuses, operate quickly to clear a fault, minimizing the risk of electrical shock and fire hazards. There are several key objectives of grounding, including firstly, to protect people from electrical shock, secondly, to provide a path for fault current, thirdly, to stabilize voltage, and fourthly, to minimize electrical noise. The NEC specifies different types of grounding systems, each with its own characteristics and applications. Firstly, there's the grounded system where one of the circuit conductors is intentionally grounded. Secondly, there's the ungrounded system where none of the circuit conductors are intentionally grounded. For grounded systems, the NEC identifies several types, including firstly, the solidly grounded system where the grounded conductor is connected directly to ground. Secondly, impedance grounded system where impedance, usually a resistor, is inserted between the grounded conductor and ground. And thirdly, corner grounded delta system, which is a type of three-phase system where one of the phase conductors is grounded. The grounding electrode system is the means by which the electrical system is connected to the earth. It typically consists of one or more grounding electrodes that are bonded together. Common types of grounding electrodes include firstly, ground rods, which are metal rods driven into the earth. Secondly, ground plates, which are metal plates buried in the earth. Thirdly, metal underground water pipe, which can serve as a grounding electrode if it meets certain requirements. And fourthly, concrete encased electrodes, which are grounding electrodes encased in concrete. The NEC specifies requirements for the size and installation of grounding electrodes, as well as the methods for bonding them together to form a complete grounding electrode system. Bonding involves connecting different metal parts of an electrical system together to create a low impedance path for fault current. This helps to ensure that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. The NEC specifies requirements for bonding different types of metal parts, including firstly, service equipment, which includes items like service panels and disconnects. Secondly, metal enclosures, which includes enclosures for electrical equipment, such as junction boxes and cabinets. Thirdly, metal raceways, which includes conduits and tubing that enclose electrical conductors. And fourthly, metal piping systems, which includes water pipes and gas pipes. The grounding electrode conductor, or GEC, is the conductor that connects the grounded conductor of the electrical system to the grounding electrode system. The NEC specifies requirements for the size and material of the GEC, as well as the methods for connecting it to the grounding electrode and the grounded conductor. The equipment grounding conductor, or EC, is the conductor that connects the non-current carrying metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault current to return to the source, helping to ensure that overcurrent protective devices operate quickly to clear fault. The NEC specifies requirements for the size and type of EGC, as well as the methods for installing it. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock by monitoring the current flowing in a circuit and quickly interrupting the power if a ground fault is detected. Ground faults occur when current leaks from a circuit to ground, which can happen if someone comes into contact with a live wire or faulty appliance. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line disturbances. SPD work by diverting excess voltage to ground, preventing it from reaching sensitive equipment. The NEC specifies requirements for the installation of SPD in certain types of electrical systems. In addition to the general grounding requirements in Article 250, the NEC also includes specific grounding requirements for different types of equipment and systems. Firstly, there are requirements for grounding of generators, which include portable generators and permanently installed generators. Secondly, there are requirements for grounding of transformers, which includes both distribution transformers and control transformers. Thirdly, there are requirements for grounding of motors, which includes both single-phase motors and three-phase motors. Fourthly, there are requirements for grounding of sensitive electronic equipment, which includes computers and other electronic devices that are susceptible to damage from voltage surges and electrical noise. Grounding and bonding are critical aspects of electrical safety, and it's important to follow the requirements in the NEC to ensure that electrical systems are installed and maintained properly. Proper grounding and bonding can help to protect people from electrical shock, reduce the risk of fire hazards, and improve the reliability of electrical equipment. The National Electrical Code, NEC, undergoes regular revisions and updates to reflect advancements in technology, address emerging safety concerns, and improve clarity and usability. The NEC is typically revised on a 3-year cycle, with new editions being published every 3 years. These revisions are made by the National Electrical Code Committee, a group of experts from various fields, including electrical engineers, contractors, inspectors, and manufacturers. The revision process involves a thorough review of the existing code, consideration of proposed changes, and public input. Proposed changes can be submitted by anyone, and they are carefully evaluated by the NEC committee to determine their technical merit, impact on safety, and feasibility. The NEC committee holds public meetings to discuss proposed changes and solicit feedback from stakeholders. These meetings provide an opportunity for interested parties to voice their opinions and concerns, and to help shape the final content of the NEC. Once the NEC committee has completed its review and revision process, the new edition of the NEC is published by the National Fire Protection Association, NFPA. The NFPA is a non-profit organization that develops and publishes a wide range of codes and standards related to fire safety and electrical safety. The NEC is widely adopted by state and local jurisdictions in the United States, and it serves as the basis for electrical codes and regulations in many other countries around the world. It's important for electrical professionals, including electricians, engineers, and inspectors, to stay up to date with the latest edition of the NEC and to understand its requirements. Failure to comply with the NEC can result in penalties, liability, and, most importantly, increased risk of electrical hazards. In addition to the NEC, there are other standards and guidelines that may be relevant to grounding and bonding, depending on the specific application. Firstly, there are IEE standards which are developed by the Institute of Electrical and Electronics Engineers and cover a wide range of topics related to electrical engineering. Secondly, there are UL standards which are developed by underwriters' laboratories and cover the safety testing and certification of electrical equipment. Thirdly, there are ANSI standards which are developed by the American National Standards Institute and cover a wide range of topics related to standardization and conformity assessment. It's important to be aware of these other standards and guidelines, and to consult them as needed to ensure that electrical systems are designed, installed, and maintained in accordance with best practices. Grounding and bonding are complex topics, and it's important to have a thorough understanding of the underlying principles and requirements. There are many resources available to help electrical professionals learn more about grounding and bonding, including firstly, training courses which are offered by various organizations, including trade schools, community colleges, and professional associations. Secondly, there are textbooks which provide a comprehensive overview of grounding and bonding principles and practices. Thirdly, there are online resources which includes websites, articles, and videos that cover a wide range of grounding and bonding topics. It's important to take advantage of these resources to stay informed about the latest developments in grounding and bonding technology and best practices. The NEC provides specific guidelines on the acceptable resistance values for grounding electrodes. While it doesn't mandate a specific resistance value for a single grounding electrode, it does state that if a single rod, pipe, or plate grounding electrode has a resistance to earth of more than 25 ohms, it must be supplemented by an additional electrode. This additional electrode helps to lower the overall resistance to ground, improving the effectiveness of the grounding system. In the scenario described, the ground rod has a resistance of 37 ohms, which is higher than the 25 ohms threshold. Therefore, according to the NEC, it would need to be supplemented by an additional grounding electrode to meet the code requirements, assuming there weren't other factors influencing the overall grounding system performance. The waterline ground, with a resistance of 0.3 ohms, is significantly lower than the ground rod's resistance. This indicates that the water line provides a much more effective path to ground. However, even with a low resistance waterline ground, the NEC typically requires a supplemental grounding electrode to ensure redundancy and reliability of the grounding system. The primary reason for requiring a supplemental grounding electrode is to provide a backup grounding path in case the waterline ground becomes compromised or disconnected. Water pipes can be susceptible to corrosion, damage, or modifications that could interrupt the grounding path. By having a supplemental electrode, such as a ground rod, the electrical system remains grounded even if the water line connection is lost. The NEC emphasizes the importance of bonding all grounding electrodes together to create a common grounding system. This means that the ground rod, water line, and any other grounding electrodes must be connected together using appropriate bonding conductors and connectors. Bonding ensures that all grounding electrodes are at the same electrical potential, minimizing the risk of voltage differences and circulating currents. It also helps to create a more effective path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices. In addition to the NEC, local codes and regulations may have additional requirements for grounding and bonding. It's important to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes. Local codes may specify different resistance requirements for grounding electrodes, or they may have specific rules for the installation of grounding systems in certain types of buildings or occupancies. The effectiveness of a grounding system depends on several factors, including firstly, the type and size of the grounding electrodes, secondly, the soil conditions, thirdly, the depth of the electrodes, and fourthly, the bonding connections. Soil conditions can have a significant impact on the resistance of grounding electrodes. Sandy or rocky soils tend to have higher resistance than clay or loam soils. The depth of the electrodes also affects their resistance. Deeper electrodes typically have lower resistance because they are in contact with more conductive soil. Proper bonding connections are essential to ensure that all grounding electrodes are effectively connected together. The grounding electrode conductor plays a crucial role in connecting the grounding electrode system to the electrical system. The GEC must be sized appropriately based on the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the GEC based on the size of the service entrance conductors. The GEC must be installed in a manner that protects it from physical damage. It should be run as directly as possible to the grounding electrode, and it should be securely fastened to the building structure. The point where the GEC connects to the grounding electrode must be accessible for inspection and maintenance. In some cases, it may be necessary to install multiple grounding electrodes to achieve the desired resistance to ground. The NEC allows for the use of multiple grounding electrodes, and it provides guidelines for their spacing and installation. When multiple grounding electrodes are used, they must be bonded together to create a common grounding system. The NEC specifies that the bonding conductor used to connect multiple grounding electrodes must be the same size as the GEC. The purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly clear the fault. A properly grounded electrical system helps to protect people from electrical shock, reduce the risk of fire hazards, and prevent damage to electrical equipment. Grounding also helps to stabilize voltage and minimize electrical noise, which can improve the performance of sensitive electronic equipment. The National Electrical Code, in Article 250, addresses grounding and bonding requirements extensively. Section 250.4 provides general requirements for grounding and bonding. Section 250.24 covers grounding service supplied alternating current systems. Section 250.50 discusses grounding electrode systems. Section 250.52 outlines the types of grounding electrodes. Section 250.66 covers grounding electrode conductor sizing. Section 250.104 provides bonding of metal water piping and other metal piping. Section 250.130 details equipment grounding conductor connections. It's crucial to consult the latest edition of the NEC and local amendments for specific requirements related to grounding and bonding in any electrical installation. In summary, while a water line with a low resistance like 0.3 ohms is excellent, the 37 ohms ground rod should be supplemented. Always reference the latest NEC and local codes.